Welcome to the ePathshala lecture series in computer science. We are dealing with the course computer architecture. So, this module is on multiple issue processors. So, the previous module itself we looked at multiple issue processors. This is a continuation of the previous module where we will discuss about the VLIW style of architectures and also point out the complexities and the design issues involved in such architectures. So, if we look at the need for multiple issue processors, in spite of the hardware and software techniques that we have been using for exploiting instruction level parallelism, it is not possible for us to reduce the CPI below 1. The ideal CPI value that we can get with a single issue processor is only 1. So, if we have to look at reducing the CPI below 1, we will have to look at issuing multiple instructions every clock cycle. So, if we issue multiple instructions every clock cycle, then we can look at achieving a CPI value of less than 1. Now, in order to do this, we have to look at multiple issue processors. So, the characteristics of multiple issue processors is summarized in this table, which we have already seen in the previous module itself. So, if you look at these, there are basically two flavors of multiple issue processors. You have the Superscalar processors and the VLIW architectures. Superscalar processors are of two types. You have a statically scheduled superscalar and a dynamically scheduled superscalar. A superscalar processors basically decide on the fly how many instructions can be issued. So, the issue is decided at hardware and how many instructions can be issued. If you look at a statically scheduled superscalar, more importance is given to the compiler here. There is more burden on the compiler. So, you will have to check whether any dependencies exist between instructions in the issue packet, and if there is any dependence between the instruction in the issue packet and the one that is already available in the pipeline. The hazard detection is basically done by hardware, but it does an in order execution. So, a statically scheduled superscalar requires significant compiler assistance to achieve good performance. The compiler does most of the work of finding and scheduling instructions for parallel execution. In contrast, a dynamically scheduled superscalar requires less of a compiler assistance, but has significant overhead in terms of the hardware. A dynamically scheduled superscalar basically does out of order execution with a dynamically scheduled algorithm like Tomasulo. Now, an alternative to this superscalar approach is the VLIW style of computing. So, in this case, an alternative is to rely on compiler technology in order to minimize the potential hazard stall and actually format the instructions in a potential issue packet and issue them together, so that the hardware has minimal work to do with this, and the compiler has the burden of detecting dependencies and forming them into issue packets and all that. So, the compiler ensures that dependencies within the issue packet cannot be present, and if at all there is a dependence present, it indicates where the dependence can occur. So, instead of the hardware doing the hazard detection, we look at the compiler doing the hazard detection and tries to put instructions which you do not have any dependencies together in a packet. So, the issue is also static and the hazard detection is also done by the compiler. So, this style of architecture is normally called VLIW, and the reason for doing this is we know that the compiler technology offers potential advantage of simple hardware or simpler hardware while still exhibiting good performance through the extensive compiler technologies that exist. This achievement of the compiler in order to exploit parallelism is reflected in the architectural approach called the VLIW style of architectures, where VLIW stands for very long instruction word. So, in the VLIW processors, instructions are scheduled by the compiler and you have a fixed number of operations which are formatted as one big instruction called a bundle. Say for example, you may decide to have 2 memory operations, 2 floating point operations and 1 integer operation. So, that forms a bundle that is decided at design time, and every bundle consists of these 5 instructions to two memory operations, two floating point operations and one integer operation, for example. If the number of words that you put into a bundle is less, say about 3 operations, it is called a long instruction word. So, VLIW basically indicates that you have a very long instruction word, because basically you are trying to combine multiple instructions together, you are forming it into a bundle or a packet. So, the instruction length increases, and that is why it is called a VLIW, very long instruction word. So, there is a change in the instruction set architecture. So, earlier you know that a program counter, the program counter value points to one instruction or one operation, but now it points to one bundle which consists of multiple instructions or multiple operations. So, VLIW operations processors, when the compiler issues these bundles, forms these bundles, the architecture simply issues this bundle every clock cycle. So, it uses a fixed format, and because of the fixed format, decoding operations can happen in parallel. There is always a specific slot allotted for each of these different types of operations. Memory operations are always encoded in one place, floating point operations are encoded in another place, and so on. So, because of this fixed length encoding, you can do decoding in parallel. Also, you should make sure that there are enough functional units for the various types of operations that can be issued in parallel. While you are designing the bundle itself, you will have to make sure that you have enough number of functional units to handle these instructions, which will have to be executed in parallel. And you also look at pipeline functional units, and there are several machines which make use of this architecture, including the IA64 architecture and the TM32 architectures. So, if you look at the VLIW processors, generally the goal of the hardware design in any case is to reduce the hardware complexity and also to shorten the clock cycle time for both better performance, and also you would like to look at reducing the power requirements. These are generally the goals of your hardware design. Now, how do we handle it here? Now, how does VLIW handle this reduction in hardware complexity? In the case of your VLIW style of architectures, the multiple issue hardware is less, because most of the hazard detection issue, everything is handled at the compiler level. The multiple issue hardware is less complicated. There is no dependence checking for instructions within a bundle, because the dependence checking has already been done by the compiler. You can have fewer paths between the instruction issue slots and the functional units, and you can have simpler instruction dispatch, and there is no out of order execution. There is no instruction grouping happening here. So, ideally there is no hazard checking logic that has to be present in your hardware. So, all this leads to reduction in the hardware complexity, and because of the reduction in the hardware complexity, obviously cycle times get reduced and power consumption gets reduced. So, if you look at the compiler support, because even though the hardware is less complicated, the compiler has to be even more talented and even more aggressive to handle all the issues that the hardware has not handled now. So, in order to increase the compiler support to increase ILP, the compiler creates each VLIW word, which consists of a number of instructions put together as a packet, and you need to have a good code scheduling, which is better than with the in-order issue superscalars, because the entire onus is on the compiler. The scheduling that the compiler does should be even better than what a compiler did for in the case of a in-order issue superscalars. So, techniques for increasing ILP, we have already looked at different techniques for increasing ILP. We have looked at the loop unrolling technique, we have looked at software pipelining technique, where we try to schedule instructions from different iterations to form a kernel. You can also look at aggressive inlining, where functions become part of the caller code, and you can also look at advanced techniques like trace scheduling, where instead of looking at a sequential flow, the exact sequence of operations, for example, I have an if then else case, so or a branch instruction, it translates to a branch instruction depending on the branch taking or not. You have the actual trace that is being generated, that is being stored in a trace cache, and you try to fetch instructions based on the actual flow of instructions, not the sequential flow of instructions. So, you can also look at advanced techniques like this. So, basically because the compiler is responsible for uncovering instruction level parallelism, all these techniques are extensively used in VLIW processors, so that you are able to uncover as much parallelism as possible. Now, the VLIW depends on enough parallelism for keeping the functional units busy, because the hardware is not going to uncover any ILP here. It is the compiler which has to uncover ILP. So, obviously, you will have to uncover enough parallelism, otherwise your functional units will not be kept busy. This parallelism is uncovered by loop unrolling and then code scheduling with a single large loop body. Now, if you are able to generate a straight line code with unrolling process with a single basic block, then you can look at local scheduling techniques. But if you have to look at code beyond branches, if you have to look at code across branches, then you will have to look at global scheduling techniques, which are much more complex and involved. So, the compiler support to increase ILP detects the hardware hazards and tries to hide latencies, because hazard detection is not done in hardware, it is going to be done in the compiler. So, the hazard detection has to be handled by the compiler, and also all latencies will have to be hidden by the compiler now. So, how are structural hazards handled? Structural hazards are handled by the compiler by making sure that no two operations to the same functional unit are put into the same bundle. If they are put into the same bundle, then you know that you have a structural hazard, because both of them cannot use the same functional unit at the same time. So, those instructions are avoided in a bundle. Also, you make sure that no two operations to the same memory bank are scheduled together. So, in such case also you will have a structural hazard. So, they cannot come together in a packet. Now, if you look at the other hazards, data hazards, you make sure that there are no data hazards among instructions in a bundle, and you also look at renaming process and all that to remove all the name dependencies and thus avoid the other data hazards. And as far as control hazards are concerned, you know that a predicated execution that we discussed in the earlier modules with the help of predicated instructions or conditional instructions, they can be used to handle your control hazards, and the compiler can do static branch prediction based on the profiling of the code and based on the earlier behavior of the code. So, you can look at static branch prediction, which will try to avoid your control hazards. So, all these hazards, your data hazards, your control hazards, your structural hazards, all of them will have to be handled at the compiler level as far as possible. Now, as far as hiding latencies are concerned, you can look at techniques like data prefetching, where because you know there is a latency involved, you can go ahead and say, for example, a load instruction is going to take a long time to load data from memory. You can do a data prefetch, assuming that this data is going to be required later in your program. You can also look at doing a code reorganization, where a load which is going to take more time to execute can be hoisted above other instructions. Of course, making sure that the data flow is not affected and exceptions are not getting generated. Additional exceptions are not getting generated. Obviously, there is a trade-off here between the instruction space and the simple decoding techniques that we use, because the long instruction word that we use has room for many operations, and by definition all the operations the compiler puts in one long instruction word are independent. They can execute in parallel. Let us look at an example here, a loop that shows a simple loop which we have already seen. You have a load, you have an add, and you have a store. So, you are taking a data from memory, you are adding something to it and you are putting it back into memory. But let us assume that you will have to schedule it. See, we have already looked at the concept of loop unrolling. Loop unrolling basically gives you the option of generating a number of independent instructions. And for VLIW, this becomes even more important, because the compiler will have to have a number of independent instructions so that it can form them into the appropriate bundles. So, you should be able to uncover as much of parallelism as possible. So, loop unrolling becomes very, very essential here. So, this slide shows you a loop that has been unrolled 3 times, and we've assumed that there is a latency of 1 clock cycle between the load and the add, and there are 2 clock cycles latency between the add and the dependent store, and there is a single branch delay slot for the branch instruction. And this loop, we've assumed that it will take 11 clock cycles to execute depending upon the schedule that has been shown here, or it takes about 3.67 clock cycles per iteration. Now, what will happen if you have to schedule this loop on schedule the unroll loop in a VLIW style of architecture? Let us assume that you have these types of operations which can be put into a bundle. You have 2 memory reference instructions, 2 floating point operations, and 1 integer operation or a branch which can be scheduled in one VLIW word or a bundle. This again depends on the design that is done. It is a design issue. It is not that all VLIW processors look at this format. They can look at different formats. We will assume that you can have 2 memory references, 2 floating point operations, and 1 integer operation per clock cycle. So, how do you design this? So, let us assume that you have the first load instruction. So, when you issue the first load instruction, the subsequent operation of the first clock cycle, when you issue the first load instruction, the subsequent operation of add, which is dependent on this load, cannot obviously be issued in the second clock cycle or the second bundle, because there is a dependency, there is a dependency, and you need to have a latency of 1 for the add instruction. So, that can be issued only in the third clock cycle. Similarly, between the add and the subsequent store, we need to have a latency of 2. So, the 4th and 5th clock cycle you cannot issue any instructions. The 6th clock cycle only you can issue your store instruction. So, this is basically how the dependent instructions of one iteration can be scheduled. Now, the idea is, because you have so many slots lying vacant, the unrolling process has generated so many parallel instructions for us. So, those independent instructions can be filled up in these slots. We will see how this can be done. Say for example, I have unrolled the loop 3 times. So, I have 2 more loads which have come. So, what I do is, I have the load instructions coming in the subsequent slots. I have the load instruction here. So, if you unroll it, as you unroll it more number of times, more slots will get filled up. So, we have unrolled it say 7 times here. So, you have 7 loads. So, the first 2 slots take in the 2 load instructions. The second bundle or the second slot takes in the subsequent 2 load instructions. Remember, all the concepts of unrolling you should be able to recollect. So, when you are doing the unrolling process, you will have to do proper address modification. So, the first data, if it is loaded from 0R1, the second data has to be loaded from 8R1, that is the next data will have to be loaded. So, whatever your loop maintenance code did, we are removing the loop maintenance code. That address modification is brought into your load instruction itself. So, you can see that the address data value has changed from 0 to 8 to 16, 24 and so on and so forth. The second thing that you will have to remember is, you will have to do register renaming. So, you can't use the same registers, in which case you will have a name dependency and they are not independent instructions anymore. So, you will also have to do a register renaming process, so that each instruction becomes independent of each other. So, only if they are independent you can execute them in the same bundle. So, you have 2 loads given scheduled for the first bundle, the next 2 loads scheduled for the second bundle, the next 2 loads scheduled for the third bundle, and by the time the latency of 1 between your load and your add has finished, so you can schedule your your add instruction there for the 2 loads issued in the first clock cycle. The 2 adds can come in, so on and so forth. And similarly, when you look at the store instruction, you find that you will have to leave out 2 bundles after the first add. So, your first 2 stores come after 2 clock cycles, and you complete the schedule. So, and in order to remove the dependency between your sub instruction, the last sub instruction, see how your address has been modified for the last sub instruction, because you have unrolled it 7 times, and that again has a dependency with your branch instruction. So, to remove that dependency, you are trying to push it ahead. So, this is how you do a scheduling. So, this type of scheduling we are already familiar with. We saw how a loop can be unrolled and it can be scheduled for a single issue processor. without any stalls. Now what we are trying to do is, it is a multiple issue processor that we are looking at. It is a VLIW style of architecture that we are looking at, so that we will be able to issue multiple instructions in every bundle. And in order to generate enough number of parallel instructions, we obviously have to look at techniques like loop unrolling, which will give you a lot of parallel instructions which can be scheduled in these slots. Now with this, we see how you can schedule the instructions properly, and it comes up to an average of 1.3. So you get a speed up of about 2.8 for the VLIW style of architecture. So this is the concept of VLIW. So it's the compiler's responsibility to unroll the instructions, identify parallel instructions, form them into bundles, and then issue these bundles to the processor to execute. So the first clock cycle, the first bundle consists of 2 instructions in our example. The second bundle also consists of 2 instructions, but if you look at the third bundle, it consists of 4 instructions where you have 2 loads, you have 2 adds, only the integer slot goes vacant. So as you are able to identify parallel instructions or independent instructions to fill into all these slots, better utilization of the functional units will be done. Now this EPIC architecture, the IA64 architecture, which follows the EPIC philosophy, is a direct outcome of the VLIW style of architectures. EPIC is a programming style which indicates explicitly parallel instruction computing, which was basically derived from the VLIW style of architecture. We will not get into too much details of the EPIC style of architecture, but I just say that Itanium IA64 architecture is based on the EPIC style of architectures. So where you have, because it is a VLIW style of architecture, we have a number of instructions put into bundles. So you have 128-bit bundles, you have 3 41-bit instructions per bundle, you have 2 bundles which can be issued at any point of time. And as far as the registers are concerned, you have 128 integer and floating point registers, you have 128 additional registers for loop unrolling and similar optimizations, and you have 8 indirect branch registers. There is extensive support for predication. You have a number of other miscellaneous registers. So all these are characteristics of IA64 architecture. This IA64 architecture, the microarchitecture seem complicated, some with support for some features of out of order processors. As I already pointed out, we are not getting into the details of the IA64 architecture, but just to give you a feel of this style of architectures, I have just listed down some of the features of the EPIC style of architectures. So here not all instructions in a bundle need stall if one stalls. So basically what will happen is, even if one instruction stalls, everything will have to stall, but you do not have to do that, because there is some amount of dynamic scheduling that is done. A scoreboard which is similar to our Tomasulo's dynamic scheduling algorithm keeps track of dependency between the instructions and when the source operands are produced for the dependent instructions. And you have multi-level branch prediction support, you have extensive support for predication, and you have what is called rotating registers in order to support your pipelining, software pipelining, and you also have special hardware for register window overflow detection, and you also have special instructions for saving and restoring the register stack. So all these are some of the features that are present at the microarchitecture of your IA64 architectures, which follows your VLIW style of architectures. Now, having discussed the basic concepts of VLIW style of architectures, we will just briefly look at what are the problems associated with the VLIW style of architectures. First of all, what are the technical problems? Obviously, there is an increase in code size because we do a lot of loop unrolling, we do ambitious loop unrolling, and whenever instructions are not full, all the unused slots go as no ops, and they are unused functional units, but they are still wasted bits in your instruction instruction format. So all that leads to increase in code size. An instruction made to be left completely empty if you are not able to find any operation to be scheduled in that bundle. In order to avoid this increase in code size, people have looked at different compression and decompression techniques where you can encode your instruction format, store it in a compressed form, and when it is brought to memory after it has been fetched from memory, you can expand it, decompress it and use it. So, that way you can reduce the complexity associated with your increase in code size. The second important thing is we are looking at synchronous operations. Most of the cases, at least the early VLIW style of architectures looked at a synchronous mode of operation or a lockstep mode of operation. So, if one instruction does not complete in a bundle, then you cannot issue the next bundle of instructions until everything else finishes in the first bundle. Now, a stall in any functional unit pipeline may cause the entire processor to stall. Now, these days of course, the recent VLIW processors do some amount of dynamic scheduling also, where the functional units operate a little more independently. So, the compiler is used to avoid hazards at the issue time, but the hardware checks allow for unsynchronized execution once the instructions are issued into the hardware. The other logistical problems that you have is the binary code compatibility. Because the instruction opcode is generated based on the instruction set architecture as well as the latency of the functional units and all that, it is not possible to have binary code compatibility. So, that is one drawback of VLIW processors. So, if you have to migrate between successive implementations or between implementations, you will have to do a recompilation process depending upon the latency of the functional units and the number of functional units that you have. That is another problem. So, the solution to this logistical problem is normally you try to look at object code translation or emulation, or generally temper the strictness of the approach so that binary compatibility is still feasible. Now, what are the advantages of Superscalar over VLIW? Superscalar architectures definitely have an advantage that the old codes still can run. So, like those tools that we have used come as binaries and we have used for long. The hardware detects the instruction pair as a legal dual issue pair, and if they cannot be issued, it will stop them. All this is possible if you are looking at Superscalar, and if you find that they cannot be issued, they will be run sequentially in the case of your Superscalar. And there is little impact on code density because you do not have to fill all the slots. You can decide, there is no question of filling it with no ops. You can decide how many instructions will be issued, and the subsequent instructions will automatically get executed depending upon the dependence. Compiler issues are very similar because you still have to do instruction scheduling anyway, and dynamic issue hardware is there. So, the compiler does not have to be too conservative in the case of your Superscalars. So, if you look at the comparison between Superscalars and VLIWs, Superscalars have more complex hardware for instruction scheduling. They need more instruction slotting or out of order hardware. They need more paths between instruction issue structure and the functional units, and the possible consequences of that is of course slower clock cycle times and more chip real estate, and of course more power consumption. Those are the drawbacks again associated with your Superscalar. Whereas if you look at your VLIW style of architectures, VLIW architectures have more functional units if there is support for full predication. There is slower clock cycle times, more chip real estate and more power consumption. VLIW of course, as I told you, has larger code size. This is the estimate of your IO64 code. There is about an increase of 2 to 4x over the x86 architectures, and the consequences are increase in the instruction bandwidth requirements and decrease in the instruction cache effectiveness. VLIW of course requires a more complex compiler where Superscalars can be more efficiently executed in a pipeline independent code. So, to summarize, we have looked at the need for multiple issue processors. We have looked at the second flavor of multiple issue processors, namely the VLIW style of architectures. So, in the case of your VLIW style of architecture, the hardware is not so complex. The compiler becomes more complex because the compiler is responsible for uncovering parallelism. So, what the compiler does here is it identifies independent instructions by using different techniques like loop unrolling, software pipelining, predication and all that, and it forms the independent instructions into predefined bundles. These bundles are issued into the hardware for execution. So, the hardware does not do any hazard detection. The entire hazard detection and issue is done by the compiler. The compiler has to be complicated and it has to use different techniques for exploiting ILP. Of course, VLIW style of architectures have certain advantages as well as certain disadvantages compared to superscalar processors. Thank you.